This video explains some important mapping concepts so that you can use GIS more effectively. You've seen lots of maps. Some are good and some not so much. So what should be on a map page? Careful map design conveys your map message clearly to the map reader. A good map will have a title. A title is a must when you create your own maps in GIS. Otherwise, map viewers might not recognize the location or understand what's being depicted. The title explains to the reader what purpose your map serves. A map legend explains the symbols on the map and must be included for all but the most elementary maps. A map reader will not understand the symbols without a guide. Do the red lines represent roads or railroads or polluted streams? The legend will explain. What about those different sized dots? Well, the legend is going to tell you what they mean. A scale is required on a map so that the reader can understand the scope of the map and the distances between places. All good maps have scales. How far between those cities? How large is that lake? A map scale can be used to provide the answers to those questions. A north arrow or a grid of latitude and longitude lines called a graticule should be included on every good map. These items orient the reader to directions on the map. Because we're accustomed to seeing north at the top center of most map pages, sometimes it's absent, but it's really good practice to go ahead and include a north arrow or a graticule. Your finished map pages in GIS should include these basic elements. The idea of careful map design is to provide information that's necessary to the map reader without a lot of extraneous elements on the map page. Scale is the ratio of map distance to ground distance and can be expressed or presented using three different techniques. The first one would be a simple word statement like 1 inch equals 405 miles. A map reader measuring an inch between two cities, that those cities are 405 miles apart on the ground. A graphic scale uses a bar or some other symbol with divisions noting distance. These graphic scales are usually the best ones for GIS maps. Why is that? Well, GIS maps are often only in digital format. They might get emailed, they might get printed at different scales. A graphic scale enlarges or reduces with the map as it's enlarged or reduced, so it remains accurate. Finally, a representative fraction can indicate scale. Note that no units are required for a representative fraction. With the representative fraction of 1 to 25 million, measuring 1 hand width or 1 inch on the map would translate to 25 million hand widths or 25 million inches on the ground. In most cases, of course, map readers would convert the 25 million hand widths or inches to something more understandable like miles. Large and small scale are another use of the concept of map scale. In this context, large scale maps zoom in so features are larger and more detail can be seen, while small scale maps zoom out with smaller features and less detail. A scale map of central Boston, for example, might show most streets and important buildings, while a small scale map would zoom out to eastern Massachusetts and show all of Boston as a mere dot and only major highways leading to the city. Because you can easily zoom in or zoom out, scale might seem to be unimportant. However, if you zoom in to GIS data, you may find that lines or polygons begin to look blocky with sharp corners. Why is that? Well, GIS data is created at specific scales and is appropriate for only limited zooming in or zooming out. For example, GIS data of eastern Massachusetts created at a scale of 1 to 25 million would be unsatisfactory when zoomed in to 1 to 5 million. On the other hand, data created at a scale of 1 to 5 million would appear messy and crowded when to 1 to 25 million. Satellite or aerial photos also have appropriate scales for their use. If you zoom in too much, you begin to see pixels that comprise the image. GIS data therefore must be selected at a scale appropriate for your finished map. Map generalization refers to the process of simplifying the real world for representation on a map. No map can show all of reality. For example, a map of the Marshall University campus the size of a sheet of notebook paper might show the buildings and sidewalks, major streets, but would not likely show underground utilities, light poles, parking meters, landscaping, trees. So the purpose of the map and the scale of the map forces the cartographer to generalize. One principle of generalization is selection. what is important that needs to be depicted, and what can be left off the map to avoid clutter. As the scale changes, selection and omission also change. A map of central Boston might show tourist attractions, while a map of eastern Massachusetts simply shows the roads needed to get to Boston. In order to emphasize some features, they might need to be exaggerated, which is another kind of generalization. An important highway might be shown as a thick red line. Consulting the scale might reveal that the line thickness represents a mile or more on the ground. No road is that wide, but the cartographer exaggerates to illustrate the highway's importance. A third technique of generalization is smoothing. On a small-scale map, a coastline might be a smooth curve, while a large-scale map zooms in to show more details, such as man-made docks or natural jaggedness of the coastline. Again, the scale of the map and the cartographer's purpose drive the amount of smoothing. Now, before there was GIS, generalization was accomplished by the cartographer who, as he drew the map, would smooth, exaggerate, would select using pen or paper. But in a GIS world, generalization depends on the scale needed for a particular project. GIS data is created with different amounts of generalization depending on the scale it's needed for. For example, GIS data created at a scale like 1 to 1 million will be more generalized than data created for larger scales like 1 to 25,000. GIS data therefore is created at different scales and with varying